Hello, my name is David Sutterer, and thanks for stopping by for a run-through of my virtual psychonomics poster. The project I'm going to talk to you about today is motivated by recent work finding that multivariate patterns of alpha band activity on the scalp can be used to track the focus of spatial attention, both during initial study and later on during memory retrieval. So in light of this work, we wondered whether these patterns of EEG activity can be used to provide new insight into the mnemonic processing that takes place as a participant studies a list. And specifically, attention is thought to play an important role in producing the primacy effect, or increased memorability of items from the start of a studied list, while precisely how attention supports this effect remains an open question. Here we used a spatial free recall task to examine two possible ways in which covert spatial attention could contribute to the primacy effect. The first possibility is that the fidelity of covert spatial attention is enhanced for primacy items because attention is undivided at the start of the list. While the second possibility is that the spatial representation of the primacy item is refreshed throughout the list. To answer this question, we recorded EEG activity while observers completed a spatial free recall task in which they memorized short lists of 5 words that were each presented in unique locations around fixation. Immediately after studying each list, observers were prompted to recall each word from the list in any order before reporting the location corresponding to that word. When we look at the behavior, performance on the task revealed a clear primacy effect for item information, such that free recall probability for the primacy word was superior both in terms of overall recall and the tendency to report the primacy item first. And we also observed a robust primacy effect for spatial source memory, such that spatial position recall was superior for both the primacy and the recency item. To determine whether alpha band activity on the scalp tracked the spatial location of studied words, we used an inverted encoding model. And so just briefly, this model assumes that alpha activity measured at each electrode reflects the weighted sum of a set of location channels that are each tuned for a different location. And just like any analysis using linear classifiers, the way this works is we partition the data into a training and test set, and then we use the training data to estimate the relative contribution of each of these tuning profiles at each electrode. And then once we know the relative contribution of each channel to the response at each electrode, we can take the test set of data and work backwards using the pattern of EEG activity to estimate the channel responses when each location is studied or remembered. And so if the model works, we should see something like we do here, where we see a peak response in the channel tuned for 90 degrees when the study word was presented at 90 degrees. And now, so rather than plotting the individual channel responses for each studied word separately, we can instead just measure the average spatial selectivity for all the studied locations at each time point in the trial. So here, 0 on the y-axis reflects chance-level spatial selectivity, while higher numbers reflect better spatial selectivity. And so now the question is, how do these representations evolve across a study episode? And in line with our previous work, what we find is that alpha band activity begins tracking studied locations within about 100 milliseconds or so of target onset and extends throughout the entire study episode. We also find that alpha band activity tracks these studied locations well into the blank period following the study item, so up to a couple seconds after it was presented. Critically, when we compared the spatial selectivity for each individual list position, we found no difference in selectivity either during study or during the post-stimulus interval, showing that the selectivity of alpha band activity was not enhanced for the primacy item. So to test our second question of whether the location of the primacy item was perhaps instead refreshed throughout the list, we simply reran our model, this time training and testing on the location of the primacy item while the other list positions were studied. And when we look during the study interval, we find no evidence that the location of the primacy item was refreshed, nor did we find any evidence that the location of any other list position was refreshed during this initial study period. Critically, however, we found that only the location of the primacy item could be reconstructed during the delay following the presentation of subsequent items, suggesting that refreshing via covert spatial attention contributes to the primacy effect for spatial source memory. So to sum up, over the course of this project, we found that the fidelity of spatial attention was not enhanced for primacy items. Instead, observers redeployed attention to the primacy location between study events. And together, these findings suggest that observers strategically deploy covert spatial attention to prioritize the current item when it's on screen, and then refresh the location of the primacy item during the brief delay between study events, providing evidence that refreshing via covert spatial attention contributes to the primacy effect for spatial source memory. And thanks again for taking the time to visit my poster.